Welcome back. This is part two of our regression wisdom that we're trying to kind of understand. And we're going to focus on some outliers, and extrapolation, a couple other things to wrap up this chapter. So, the first idea that we're going to cover in this video is this idea of extrapolation. And it's very tempting to want to look at a regression line and be able to try to predict the future. Linear models give a predicted value for each case in the data, so making predictions makes sense. Unfortunately, we must never assume that a linear relationship in the data exists beyond the range of the data. I want you to think of the rat question from levels or chapter 7. The farther the new x value is from the mean x, the less we trust, or the less trust we should place in the predicted value. The further you're away from the average, the less accuracy we should expect, because it's harder to predict out into the future. I mean, think how well the weather predicts 1 week out, 2 weeks out versus 1 day out. Once we venture into new x territory, such a prediction is called an extrapolation. Extrapolations are questionable because they require the assumption that the model between the predictor variable and the response variable remains the same, even at extreme, not measured values. And that may not be the case. Extrapolations can result in erroneous conclusions. You are much better off not making extrapolations. You're much better off not making extrapolations, or at the very least, extrapolating only very slightly beyond your data. Don't get too far out into predictions because we don't necessarily know what's going to happen in the future. Things change. For example, here is a time plot of the Energy Information Administration, EIA, predictions and actual prices of oil barrel prices. So how did forecasters do? Because if you could predict the price of oil, you would be in the money. So if we were looking at this model compared to 1998, we are right here. 1998, they predicted a linear increase in price. 1 year later, the price of oil dropped. And they were like, okay, well, let's be a little more conservative. It's going to increase at a slightly more sharp place than what we thought before because it's got to go up. Well, what happened since 1999 is we saw a slight fluctuation in the price of oil. And then right around here, I would say that's about 2001, the price of oil skyrockets. Why did oil skyrocket in 2001? Well, think, this was the Iraq War. This was the World Trade Center getting attacked, the US getting attacked, and we go to war. And this massively increases our price in oil, which is not able to follow the predictions. In fact, no one can predict oil prices that are subject to the turmoil in the Middle East. And actually, current oil prices are very, very low. Now, you guys don't normally think about oil prices. You look more like gas prices. So if I pull up this chart from Gas Buddy, we can look at the blue, which is the US average price in gas. And then I also have the Detroit price in gas. That's where we live. So as we look at this, going back a month, you see that the price in oil seems to be declining. Well, would you have been able to make that prediction from 3 months ago or 6 months ago? We see that there was a massive drop in the gas price about 6 months ago, back in April. Well, I wonder what happened there. Or if we go back 9 months ago and we were thinking, oh, we're back in January or February, everything's nice and gas is at $2.49. And then magically, the world drops off. No one's driving cars anymore because it's a pandemic. Who could have forecasted that? Or if we look at 18 months, 2 years, or 4 years, 6 years, or even 10 years ago, there's so much fluctuation in these prices that if we were trying to make a model to predict, oh, prices are going to go up, we might be able to predict that, but just as likely, the prices are going to drop dramatically. Like we see, if you look at 2014, the gas price dramatically dropped from almost $4 down to almost $2. And again, we see some rises and falls. we don't want to try to extrapolate because there's a lot of unforeseen factors. All right, back to the notes. Extrapolation is always questionable. When the predictor variable in the model is time, it becomes very tempting to predict the future. Just be cognizant of the dangers inherent in that attempt and expect to be wrong. Consider a table of mortality rates from the age 21 to age 50. There's most likely a linear relationship between increasing mortality, how long you live, predicted by increasing age. Do you think the model would accurately predict mortality rates for ages 75 to 100? Is it different? Are there other factors at play the longer you live that would impact your mortality? Would it be linear? Basically, what we're saying is, if you must extrapolate into the future, at least do not expect the prediction will come true. Okay? Try to avoid extrapolation because we're going to be wrong. If you have to, just be careful. Next things that we have to look out for. Outliers. Here are two words: leverage and influence. So outlying points can strongly influence a regression. Even a single point far from the body of data can dominate the analysis. Any point that significantly stands away from the pattern created by the majority of the data can be called an outlier and needs special attention. We've seen this before. When we looked at one variable, we're like, do we have any outliers? If you do, we would report it with an outlier and then removing it from the data. We don't just throw outliers away. For another example, the following scatter plot shows that something was not kosher in Palm Beach County, Florida during the 2000 presidential election. Thinking elections came up all the time, and this is 2020. We got an election right around the corner. There is also an HBO documentary called 537 that focuses on this 2000 election.
The 2000 election was a street brawl for the presidency of the United States.
We have a dispute about who is to be the next president. Both campaigns knew it was coming down to Florida.
This is gonna...
Bush was handed this plate of voters.
All of a sudden, there are problems. It's too close to call.
This triggers an automatic recount.
The rules were changing minute by minute.
You had dimpled Chads and hanging Chads and pregnant Chads.
It was so farcical.
Al Gore won the state of Florida, but Miami made sure that at least 10,000 ballots never saw the light of day.
The election was lost in many different places, but it was stolen in Miami.
While Democrats wanted to do the right thing, Republicans wanted the win.
Stop the count! Stop the fraud!
And the recount was stopped.
It was run with evil intent, and it worked.
Break. Politics is about winning.
What happened in Miami changed this country forever.
You need to take the time to vote.
Now, you guys were too young to know this, but in 2000, there was this idea of like hanging Chads and how many votes to count. Well, if we're looking at this kind of independent relationship, we have Ralph Nader running and Pat Buchanan running. If we were looking at how many people voted for one compared to the other, in this one county, we have this extraordinarily outlier prediction of people that voted for Nader or Buchanan is way outside of our scatter plot. The red line, if we include that one unusual point, shows just how significant or influential that one outlier has into our line of best fit. It changes our slope. So a linear model does not fit points with large residuals well. Remember, residual is the y value minus the predicted value. Because they stand out from other cases, it's always a good idea to examine points with large residuals. You might learn something of importance about your data or your study. Points with large residuals have influence on your model, but not every extreme point has large residuals. If an unusual point has significant influence on your model, it will pull the model towards itself and reduce the residual. Think if you have a scatter point scatter plot, and one point that's very far away. That's going to pull our line of best fit towards it. And if you think the model is close to that value, of course it's not going to have a large residual, but it's going to be very influential. It is not enough to only look at points with large residuals in order to figure out what's making this accurate or inaccurate. A data point can also be unusual if its value is far from the mean of the x values. Such points are said to have high leverage. So we have outliers that are influential, and we have outliers that have leverage. Now, if you want to look at this beautiful picture of Archimedes, give me a place to stand and I will move the earth. That type of leverage, that force, bringing it closer together. So we say this: a point with high leverage has the potential to change the regression line. We say that point is influential if omitting from an analysis gives a very different model. So if it has leverage, it could change our model. It would be influential, slightly different, if we remove it and we get a different model from that. So influential and leverage for outliers. Think large residuals or very far from the mean, the average. So suppose we investigate the relationship between shoe size and IQ. One very large fellow might have an extreme effect on our model. The extreme, unusually large shoe size gives the large fellow's data point high leverage. Wherever the giant IQ goes, the line will follow. So in this case, if he has an extremely low IQ, no matter what our scatter plot looks like, which seems like a positive relationship, our model is going to flip. That red line is going to go towards that leverage point, that influential point. When you examine an unusual data point, you might learn something about the relationship between the variables, or something of influencing your model that might not have considered from just the model itself. So you must not simply delete unusual points. You don't just get to throw them away. You can, however, run a model with and without these points. Then discuss the two regression models to understand how they differ. If you get these unusual things, what's going on here? What might have caused this to happen? So just a note of warning. Influential points can hide in plots of residuals. Points of high leverage pull the line close to them. Points of high leverage pull the line close to them, so they often have small residuals. You'll see influential points more easily in scatter plots of the original data, or by finding a regression model with and without them. So notice, influential points may hide in the residuals. Well, what could be causing that? Well, this idea of lurking variables, things that we're not actually taking into account. No matter how strong the association, no matter how large the R-squared value, no matter how straight the line or how close the points come to being on that line, there is no way to conclude from a regression alone that one variable causes changes in the other variable. And we'll see that in a second in an example that we illustrate. There is always the possibility that some third variable is driving both of the variables you've observed. When your data is observational, more about that in chapter 12, as in the case of regression analysis, there's not a way to know if a confounding, lurking variable is causing the association in our model. Confounding is like we can't separate it out from everything else. So to exemplify this, the following scatter plot shows the average life expectancy for a country is related to the number of doctors per person in that country. And notice we have the square root of doctors per person to life expectancy in years. The more doctors, the longer people live. Strong, moderately strong, positive association. So we see a moderate, linear, positive association between life expectancy and the square root of per capita number of doctors. That's our SODs right there. Well, what else could we compare? A new scatter plot shows that the average life expectancy for a country is related to the number of televisions per person in that country. So instead of doctors, let's look at TVs per person. And we get, much better. A moderately strong, positive, linear association between life expectancy and the square root of the per capita number of doctors. Obviously, people need more TVs to live longer, right? Well, what's going on here between doctors and life expectancy, TVs and life expectancy? I mean, those seem like ridiculous comparisons that we're making. Since televisions are considerably cheaper than doctors, we'd all agree with that, and much easier to obtain, we simply need to send more TVs to countries with low life expectancies in order to improve life expectancy. That sounds good to me. That's an easy solution to solve all those third world problems of countries that aren't that have people that die earlier. Or is there something else going on? I mean, obviously, countries with higher income and higher social economic status, or SES, have longer life expectancies, more doctors, and of course, more TVs. That makes sense. Maybe we should focus our monies on is improving the standard of living in those countries than sending them TVs. One more to kind of illustrate this point. Calculating the model for the association between the divorce rate in Maine and the per capita consumption of margarine in the US, we get an extremely strong model. R is equal to 0.9922. And we get the average margarine consumption, or the predicted margarine consumption, is 1.2, or the divorce rate is 1.291 times the margarine minus 1.396. We could interpret that slope and y-intercept, of course. And we see that what's going on here? The more margarine you eat, the more likely your couple is going to get divorced. Or the less likely they are to get divorced. Is that true? Just because we have a strong association does not mean that these two, that having more margarine in your house and how you cook and how you eat leads to less divorce or more divorce. It just doesn't compute. It doesn't make sense socially. There's other things going on that may cause fluctuations in divorce rates. So working with summary values, this is the last thing. Scatter plots of statistics summarized over groups, like we saw subgroups, tend to show less variability than we would see if we measured the same variable on individuals. Remember, a collection of means, or summaries, vary less than the data from which those means were calculated. So what this means is, let's look at an example. Okay, if we compared the height and weight of males, believe it or not, this was me as I was age 26. I was close to 240 pounds. There's a strong positive linear association between weight and height in inches for men. This is a collection of all of these males' heights versus weights. Well, what we could also look at is for each height, we could just find the average weight. So if someone was 5 foot tall, we could find the average weight and use that as a specific data point. What do I mean by that? Here is individuals, and then we look at mean weights. And when we look at the mean weight instead of the individuals, we would see an even stronger association. Once we go to means vary less than individual data values. Now you're wondering, why would you go to these summary of groups? Well, oftentimes when we have big groups of data, we want to talk about the averages of each subgroup as compared to 250 or 250,000 men in the study. But notice, as soon as we go to averages, because of how averages work, there's less variation. Then it is going to change how closely our association looks like. It's going to be stronger. Means vary less than individual values. So scatter plots of summary statistics show less scatter than the baseline of the data in the individuals, which can also give false impressions of how well aligned summarizes the data. Think if you were averaging all of the polls given in a given week coming up for an election, and then we tracked the average poll, like something like Real Clear Politics does, from week to week to week, it would be helpful to see what these are all saying about who's going to win this election this year or whatever year you're looking at. But you lose the variation of the individual polls by just averaging them together. Averages could show you a trend, but you're also losing some of that information by summarizing. And there's no simple correction for this phenomenon. Once we have summary data, there is no simple way to get the original values back. Kind of like grouped frequency distribution, once the data is gone, and we can't get it back. So to wrap this all up, make sure the relationship is linear and mention that in every analysis that you do. Examine the data scatter plot and the residual plot for subsets of your data that has a different pattern. Run the analysis with and without each subset and discuss the changes. Be very skeptical of extrapolating beyond your data. Predicting the future should be left to the psychics. No sane person pays any attention to them anyways. I mean, if I asked you, what does the weatherman say the weather's going to be in 3 weeks? You wouldn't give that much credence because they're never right, because it's hard to make predictions. Look for unusual points. Unusual points always deserve attention and may well reveal more about your data than the rest of the points combined. Maybe that's where we should focus our interest on, those weird stuff. Examine high leverage points to see if they have influenced your model. High leverage points have the potential to affect your model. It is a good practice to run multiple regressions with and without the unusual data values and discuss the differences in the results. If you see anything unusual, we want to see what does that cause in our results. So treat unusual points honestly. Don't just throw them away. Don't just remove unusual points to get a model that fits better. Consider the effect of lurking or confounding variables. Never assume the association you model is causal. That does not mean there is no causal relationship, but simply cannot verify that outside of an experiment with variables, we can manipulate. So we hesitate to go to a causal relationship because we don't have a controlled experiment. Again, more about that later. When running models with summary data, say a collection of means, keep in mind that that model will appear much stronger than the comparable model with the actual data. As soon as you go to summary statistics, that lowers the variation. And finally, to verify that the data is appropriate for running a correlation and regression analysis, ensure that all of the following are true. So we need the shape of the scatter plot is linear. The variables are sufficiently unimodal and symmetric. How do we get that? Either a histogram or a normal probability plot. We know how to do that. R squared is sufficient, and properly labeled residual plots shows no pattern. We want the residuals to show no funny business. And with that, we are done with chapter 9. Got one more chapter to cover in unit 2, which is how do you handle curves? So I'll see you in chapter 10, Falcons.